Now on to our next example of optimization. This will be example 2. I'm going to change it so that it is for future. So we're going to find the point P on the line y equals 3x that is closest to the point 50, 0. What is this least distance? Prove your assertions analytically. Okay, so let's draw a diagram and get some labels on our graph here. So diagram and variables, that's your first mission. Now I'm not going to draw this to scale, but you get the general gist of it. So you have a line y equals 3x, which we all know looks like that. It goes through the origin. So this is y equals 3x. And you have a point way out here, which is 50 and 0. So I'll put it out here. So over here is 50 and 0. And we want to find a point on this line, x comma y, such that the distance from that point, xy, to that point 50, 0 is minimum. So the distance is right here. I'm just going to put distance right here. Actually, I'll just call it little d. There we go. Okay, so I've got my distance, I've got my point x and y, which is right here, and I've got my line y equals 3x. So I've drawn a diagram, and I have everything labeled. So now I need to come up with an objective function. So my objective function well, they tell us right here. They say use d equals little d squared right here. And that's actually very common in distance problems to not use distance itself. Distance itself actually requires a giant square root, and that's annoying. So we're going to actually minimize the distance squared, but if you minimize the distance squared, then you've also minimized the distance. See? It all works out. Okay, so what is capital D? So capital D of xy is the distance squared. So if you think this is x and then this is x1. So you learn this in algebra class. So distance squared is x minus x1 squared plus y minus y1 squared, right? Where x1 and y1 are the points and xy are the other points, and then you go from there. So you learn that in algebra class. Now we already know that we want the point 50 and 0. That's one constraint. So you'll notice there's way too many variables going on there. I mean, technically there's 1, 2, 3, 4 variables, but there won't be in just a second because we're going to find some constraints because boy are we constrained. All right, so first constraint is that our point x1, y1 is 50 and 0, right? And then we're also constrained by the function y equals 3x. So we can use these two pieces. So I can say, okay, distance squared, which is capital D, oh, I'm not even going to write that. I'm just going to write d of xy because I don't really care anymore that it's distance squared. I'm just going to write, this is x minus 50 squared plus y minus 0 squared. Which means I'm not even going to bother writing without minus 0. And then what's more, I know that y is equal to 3x. So I can say this is x minus 50 squared plus, and then this y is a 3x squared. Done. Crazy enough, but that's d of x right there. Oh, and this was step 4 that I was doing right there. I lost my room to say that. But this is step 4 right here. I'm using the constraints to get only one variable. Get only one variable. Sorry, I got to sneak it in there. But that's what I'm doing. Boom. Oh, my squared got lost. There's a squared there. All right, so great. I now only have one variable. Now you can distribute this if you want, but you kind of don't have to because all we're going to do is take the derivative of it, and this is a pretty easy derivative to take. So it's your choice. But before I go off and do that, I don't want to forget my effective domain. So I want to look at the x values and think, how am I restricted? And the answer is you're not, right? You can actually let x go from negative infinity to positive infinity. You can let it ride along this line. As a matter of fact, I have a graph pre-drawn for you so you can see it. So you can see there's the point 50 and 0. There, that's better. So you can see the point 50 and 0, and then I've got this point over here, and it can kind of go wherever it wants, negative and positive. I mean, I'm just restricting it from negative 20 to 20 just for my own, sanity's sake right here. But technically, you didn't have to. You could just keep dragging it whichever direction you want. Okay, so that means that I can go from negative infinity to positive infinity for my effective domain. So that gets me right down here. Effective domain is for the x, which is the only thing I care about, because that's the only variable left in my D, which is negative infinity to positive infinity. Okay, so step 6. We're going to find the derivative. So find the first derivative, and the first order critical values. Okay, so this won't be too bad and not too difficult to find. So we're going to take our d of x right here, and we're going to find our derivative. So I guess I'll do that in green. So d prime of x is equal to 2 times x minus 50 to the 1 times the derivative of x minus 50, which is 1, right? So chain rule, plus 2 times 3x to the 1 times the derivative of 3x, which is 3. So I'm using chain rule right there. So that's 2 times x minus 50 plus 6 times 3x. That'd be 2x minus 100 plus 18x, which is 20x take away 100. There's the first derivative, d prime of x. All right, so that's the derivative part right here. So then let's find the critical values. So crit values. To find the crit values, the first order ones at that, right, we don't care about concavity for this right now. All right, so to find the first order crit values, I'm going to set that d prime, which is 20x minus 100, equal to 0. This can't be undefined because it's a line, right? There's no denominator, there's no trig functions in this, like tangent or anything like that. So that would mean that 20x equals 100. That would mean x equals 5. That is the only critical value we have. All right, step 6 is done. Right? Got our critical values right there. Critical value. So then step 7, we need to use a method of calculus in order to prove that this is the minimum maximum. We were looking for the minimum. Use method of calculus to prove the minimum, right? To prove min-max. Although we're trying to prove minimum in our particular case. So which method are we going to use? Well, we have an open interval for starters, and this second derivative is hecka easy to find, so we are going to use the second derivative method again. So the second derivative method is really easy on this one, because the second derivative, d double prime of x, would be equal to just 20, right? Well, 20 is positive no matter what x value I put in. That means that it's concave up, and since it's concave up, that means that the critical value, so x equals 5, must be equal to a minimum. Must be a minimum, right? Since it's concave up, that critical value will be at the bottom of that concave uppedness, right? And it'll cause there to be a minimum. Wonderful. All right, so we've proven that there is a minimum at x equals 5. Lovely. The only other thing we have to do is it always pays to go back and double check your problem and make sure that you've answered all the questions. So we found the point. Oh, we didn't find the point. We found the x value, but we didn't find the point. Okay, so there you go for x. We know what happens at x equals 5. So what's the y value? So to find the point, we're going to need that y value. So let's go back. So we need to find the y value to get the point. Well, remember, we're going to go back to our constraint right here. So we'll go back to step 3 in the constraint. Y equals 3x, which means y equals 3 times 5, which is 15. So now I have the point, which is the point P with the minimum distance is 5 comma 15, has the minimum distance. Then they also asked for what that minimum distance was. Well, the minimum distance would be, we would have to go back and find distance using this function right here. But remember, this is distance squared. So we would take the square root of this. So that minimum distance itself, we would take the point 5 and 15 and plug them back in. Right? It has minimum distance, and the minimum distance is, let's see here. So d equals the square root of d squared, which is the square root of, let's see, x, which is 5, take away 50 squared, plus 3 times x squared. So 3 times 5 squared. So we would use a calculator to find what that is. Let me grab a calculator and I'll find it. Actually, I think I can just grab Desmos. That's the beautiful thing about Desmos. So I'm going to take square root, so SQRT, parentheses, 5 minus 50, parentheses, squared, plus, and then 3 times 5 is 15, parentheses, squared. And it tells me the minimum distance is 47.434 units. So I would go put that in there. And again, it's because I have to do 43.44 roughly, right? There's the minimum distance. So, and the reason I'm doing that is because it asked. It asked, what is this least distance? So that's what it is. This is not distance. This was distance squared. So I just took the square root of that to find the minimum distance right here. I substituted my x value in. So I went to step 3 to find the y value right here to get the 15, and then step 4 to find that minimum distance, right? So this was step 4, to find that minimum distance.